Okay, so welcome everyone to our weekly seminar. Today's speaker is Dr. Frédéric Galliano, who is going to talk us about the recent advances on interstellar dust in nearby galaxies. But briefly, first, before starting about something about Dr. Galliano. So he received the PhD in 2004 from Saclay. And after that, he was first a postdoc at the NASA Goddard Space Flight Center until 2007, and at the University of Maryland from 2007 to 2008. Then in 2008, he was finally hired as a staff researcher at Saclay. Dr. Galliano is an expert in the ISM properties of nearby galaxies. He has worked extensively on the interpretation of infrared space mission data, as well as ground-based millimeter telescopes. Among other projects, he has actively participated in the Dustpedia collaboration, a European Horizon 2020 FP7 project, dedicated to making a census about the dust properties of nearby galaxies. And Dr. Galliano is currently the director of the Astrophysics axis of the Graduate School of Physics at the University Paris Saclay. So thanks again for being here today, and the floor is yours.
Thank you, Carolina, and thank you, Vasilis, for the invitation. So today I wanted to give you basically a review about my main field of research, which are the dust properties of nearby galaxies. So tell you a bit what is the current status of our knowledge of this particular ISM phase, and also how the type of studies that we do in nearby galaxies can be put in perspective with what we do in the Milky Way at much higher angular resolution, and also with what we can do in the more distant galaxies where we have less information. So I will first give you a basic introduction about really what is interstellar dust and what it is important to really study it in nearby galaxies. It's an important chain, part of the chain. After, I will give you a review about the dust properties of nearby galaxies from the point of view of different observables that in different wavelength range and in different, different processes. And I will talk about cosmic dust evolution, so the way the dust properties change, evolve in different galaxies, and how is it linked to galaxy evolution. And I will finish by a few perspectives. So first, the introduction. So what is interstellar dust? So interstellar dust are small solid particles that are ubiquitous in the ISM. So they are really mixed well with the gas, and they are potentially everywhere. So they are small, so their radius typically in the ISM varies between a few angstrom, which are the size of large molecules, to a bit less than 1 micron. And so, as I say, they are well mixed with the gas in the ISM, and their composition are about 2/3 oxygen-rich compounds, so essentially silicates, and about 1/3 carbonaceous compounds. And in total, they represent about 1% of the mass of the ISM, so it's a small fraction of the mass. But as I will show you later, it has an important role in many physical processes. And what I can say also is that I'm going to talk exclusively about interstellar dust properties. And you have to note that the properties of dust in the interstellar medium are quite different from the properties that you can see in circumstellar environments, so in the envelopes of evolved stars, or even in planetary environments. They are different in terms of size, composition. ISM dust is essentially amorphous, while circumstellar dust is essentially crystalline, and also, shape and composition. So the main way you see dust manifest in astrophysical observation is through first the effect of emission and extinction. So if you have a cluster of stars around here and a dusty cloud in front of it, what you are going to see, so you are going to have a few photons that are going to be non-extincted, so you are going to see them directly. Some are going to be absorbed by the dust grains within this cloud, and some are going to be scattered away in another direction. And what has been absorbed is going to be re-radiated thermally at longer wavelength, so in the infrared. And so it means that when you're going to observe a typical interstellar cloud, at optical wavelength, you are going to see where you have dust, that you have a decrease of light, and so you have extinction. But on the contrary, if you observe the same region at infrared wavelengths, you are going to see an emission that comes from this thermal emission. So this very simple picture, you can put it in a more physical context by looking at the spectral energy distribution, the SED, of a galaxy. So that's the power emitted as a function of wavelength. Here you see I have highlighted the ionizing photons, range here. And if you look at a galaxy or a region in a galaxy that is large enough to encompass, a statistical mixing of stellar population and stars, you observe usually something like that. So first, you have the spectrum of the stellar population. So that's the spectrum of different stars of different masses, at a given age. And a fraction of this radiation is absorbed by the dust, by the ISM, by the dust and the gas. And what has been absorbed is going to be re-radiated at longer wavelengths. So first, you have the re-radiation by the gas. So as you see the gas, you have a continuum. So that's the free continuum. Plus, so you have some band-free transitions, and you have a lot of lines. I showed only a few. You have literally thousands of lines that are emitted. And most of the power is absorbed by the dust, and so it's also the emission from the ISM is dominated by the dust emission. And you see this red curve here is actually the thermal emission spectrum of a typical dust population. And you have those features that are emitting in the mid-infrared that are the aromatic bands, because they come from aromatic bonds within carbon molecules, usually attributed to PAH, to polycyclic aromatic hydrocarbons, but there are other candidates in the literature. After, at centimeter wavelengths, you also sometimes detect a small excess emission that corresponds to the centimetric emission of spinning grains, so small grains that rotate very fast and emit. It's a dipolar emission. And also something that I'm going to talk about, there is a phenomenon that is part of the grain emission, but that current models have trouble to explain right now. That is the submillimeter excess. And so the total emission looks like that. So that's the spectral point of view. Now you can ask yourself why it is important to understand those properties. And the main reason is that it's crucial to understand ISM physics and galaxy evolution. So first, as I told you, this extinction and emission process is everywhere. And in particular, if you are interested in star formation, as you know, it can be probed in the IR because of this dust obscuration process. So here I'm showing you the star formation rate as a function of redshift, for different populations of galaxies. And you see that especially at cosmic noon, it's really dominated by dust obscure star formation. So that's the first part. Then after, you have another important reason, it's really a microphysics reason, is that the neutral gas is mainly heated by photoelectric heating that happens on the grain. So in practice, how does it work? So if you are in a neutral ISM regions, you are going to have a photon from, OB stars that are going to hit those grains. And because these photons have a few EV in energy, so most of the radiation actually is going to be absorbed and radiated in the IR, as I told you, but a few, about 1% is going to go into the ejection of a photoelectron that is going to carry some energy away in the gas. And this electron is going to thermalize with the gas through H atom and pump, in particular, on the ionized carbon atom, which is going to give rise to, in particular, the C+ line 158 micron, which is usually, depending on the type of galaxies, but usually the brightest line in the ASM. So that's another reason. Dust is responsible for the heating of the gas in neutral regions. And those lines, yes, that are the brightest in the ASM. Another important reason is that a lot of chemical reaction in the ASM happens on the grain surface, and in particular, the formation of H2, molecular hydrogen. So you see, if you have two H atoms in the gas phase, they can eventually stick onto grain surface, usually through a van der Waals interaction, and they can migrate and form a molecule on top of the grain and then be ejected later. As you know, the formation of H2 in the gas phase is quite improbable because you need to release 4 eV of energy to actually form the molecule. While here on the top of the grain, this is taken care of. And you have another quite similar, but I mean with some different process, where you have an H atom that actually falls on the grain where you already have an H atom that is attached, and you can eject a molecule too. So you have different pathways, but most of the molecular hydrogen is formed on grain surfaces. And so it means that the efficiency of this molecular hydrogen formation is going to depend quite sensitively on the actual properties of the grains, their size, shape, and also their composition. And so that's why it is important to really have an accurate description of these grain properties. For example, when you want to model photodissociation regions. Then another one is that grains have really an important physical role in the star formation process because they shield molecules from photodissociation, and they also help to radiatively evacuate the gravitational energy. So they are important to simulate the star formation process at all scales. And also here I'm showing you a simulation of a protoplanetary disk. So you see that same disks in head-on and face-on, in the gas and in the dust. And that's only the scale where actually the two are starting to decouple, the gas and the dust. And finally, the last reason why it's really important to study dust is that usually dust-induced polarization is used to trace the magnetic field. So for example, if you look at optical wavelengths and that you have a grain that is elongated, because we often make the assumption that grains are spherical, but they have actually all kind of shape. And this type of shape is really, a prorate grain. It's a simple approximation. So basically, if you have a magnetic field like that, the grain is going to rotate in a plane that is perpendicular to this magnetic field. And if you look at the radiation from a star in the background that emits unpolarized light, the grain, because of its orientation, is going to have a polarization effect. And you are going to see essentially a polarization that is parallel to this magnetic field. So if you look at optical visible wavelengths. Now, if you look at infrared wavelengths, or even up to the sub-millimeter, you are going to see this time not the radiation from the background star, but the direct emission from the grain. And the same thing happens for the same type of grain, except that now the polarized emission is going to be perpendicular to the magnetic field, because it's going to be essentially along, the long axis of the grain. And so that's why with the polarized emission in the infrared, you can make these maps of the magnetic field in the Milky Way, so that's the galactic plane from the Planck collaboration. And I'm going to talk about nearby galaxies, but the Milky Way point of view is important for all these type of studies. So in the Milky Way, that's where you get the best linear resolution, because that's the closest to us. It's also where you have the most comprehensive observable set, because that's, again, a matter of proximity. So that's where you have the best sensitivity. And so that's why, historically, observations of the Milky Way have always been used, as the main constraint to build dust models. And at the moment, all the dust models that we use are all constraints on observations of the Milky Way. But the problem with the Milky Way that it's a special case. It's a spiral galaxies with solar metallicity, with a quite moderate star formation rate. And so it means it doesn't allow us to understand what are the effects of these parameters, morphology, metallicity, and star formation rate on the dust properties. And that's why nearby galaxies are interesting, because they are close enough to give us enough angular resolution and sensitivity to really do some detailed studies, but they give us access to a much wider diversity of physical conditions. So in particular, the gas fraction, the metallicity, the star formation activity. If you go from dwarf galaxies, irregular, that have a low metallicity and are very gas rich, to normal spiral galaxies that are intermediate, up to elliptical lenticular galaxies that are on the opposite, have a high metallicity and are quite gas poor, you can really build an evolutionary sequence and try to understand how dust properties vary. And if you look at the diversity of nearby galaxies, so in really the close volume around us, here I'm showing you a diagram of the distance from us. So you see, and here it's the metallicity. And I've converted the distance into a linear resolution that we get with this Spire instrument on, in the Herschel satellite at 250 micron, because that's quite a unique constraint. If we want to really study the dust emission, we need a good coverage at this wavelength. And at the moment, Herschel is really the one that could give us this coverage at this wavelength with the best sensitivity and the best angular resolution. And so here you are at the Milky Way outskirt. So in this region, it's where we start having nearby galaxies. This distance is where we stop resolving individual clouds, typical, a few parsec size. And so you have only essentially the LMC and SMC, so the Large Magellanic Cloud and Small Magellanic Cloud, that are, our satellite dwarf galaxies, where we can, at these wavelengths, conduct studies where we can actually resolve molecular clouds. But there are also, it can also be interesting to be able to resolve molecular complexes. So large ensemble of molecular clouds of typical size of about 100 parsecs. And if we want to do that, we have more objects to do that. So I don't show all the nearby galaxies because there are, in the volume I show here, there are a few thousands, but I show you a few that are quite representative. And here we start having different types of galaxies, normal metallicity spirals and a few dwarf galaxies. And we even start having objects that help us to understand what happens at extremely low metallicity, so below 1/10 solar. Because metallicity, so the mass fraction of heavy elements, is really an important parameter for the ASM, because if you decrease it significantly like that, you are really going to change the balance between the different coolings. You are going to decrease the abundance of oxygen by a factor of 10. So you are going to have different channels for heating and cooling. And you are also going to decrease the amount of dust, and so the amount of shield screening, things like that. So I'm going to discuss that later. And after, you also have a lot of galaxies where you can't necessarily resolve molecular complexes, but you still have some spatial information. So you can get a lot of statistics and see global trends, how the dust properties vary with environmental conditions. And among these galaxies that have different types, you also have some that are starbursting, so you can really probe different star formation activities, and you even have a few that have AGNs, so you can also, try to understand what is the effect of an AGN on the dust properties, and also use AGN as a background source to conduct absorption studies. So now I'm going to talk about a bit more about the touch properties. So I'm going to start with the emission. And something that is important to understand the infrared emission by dust, it's to understand the different heating regime. So here I am showing you a typical spectrum in the IR, so that's the wavelength here, and that's the power emitted, and it's normalized by the total power. So it's normalized by the volumetric luminosity. And that's the typical emission, thermal emission by dust that I showed you later. And what's important to note is that the short wavelength part of the spectrum is due to the emission by small grains. And these small grains are small enough that their internal energy is going to be comparable to the typical energy of a photon, so a few eV. And so it means that they are going to be sensitive to the heating of single photon, and they're going to fluctuate in temperatures. So they have a quite broad spectrum because they tend to fluctuate in temperature and emit at these wavelengths. And on the contrary, if you look at the emission by large grains, so grains that have a much larger internal energy than the typical photon range, their emission is just going to look like a gray body at all sizes because they are going to be at thermal equilibrium. And the consequence of these two regimes, it's the way the dust emission is going to vary with when you are going to increase the intensity of the radiation field coming from the stars. So here I'm showing you the same type of figure, but I'm varying the intensity of the radiation field. So this parameter U, it's a global scaling of the radiation field that is equal to 1 in the solar neighborhood. So here we are at 0.1, so we are a bit lower. And when we increase this radiation field, so you see that you have a constant spectrum in the mid-IR, while the far-infrared spectrum actually evolves. So you are shifting the peak of the thermal emission of the large grains to shorter wavelength because their equilibrium temperature increases, and so on. So you see when you increase the radiation field, you have this effect. So that's the main property of the infrared emission. Now, if we look at real galaxies, what I'm going to do is I'm going to show you the STDs of a few galaxies. And what's important to note is that there are two different kind of evolutionary processes that are the one that happens on relatively long timescales of about 1 gigayear, processes that are linked to the elemental enrichment, so by the successive waves of stellar population, and that can be traced by metallicity. And other ones that happen on quite short timescales of typically a few tens of million years, processes that are linked to star formation. So those are the feedback, cloud evaporation, supernova shock waves. And you can see on galaxies actually the effect of these two different processes. So first, I'm showing you again the same type of plot, so that the emitted power as a function of wavelength in the infrared. Here I'm showing you a typical spectrum of a galactic cirrus cloud as a reference. So if you look at a galaxy like this one, 2841, which is a solar metallicity galaxy with a really moderate star formation rate, you have something like that. So what you notice is that the infrared emission really looks exactly the same as the galaxy, except that here we have the stellar continuum that has been subtracted here. So what you see is that in a quiescent solar metallicity galaxies, the dust properties really look like what you see in the diffuse ASM of the Milky Way, which makes sense. Now, if you look at also a quiescent galaxy, but a very low metallicity, like this one, you see that you have very different properties. So you see that you have lost the emission by these aromatic features here because they are probably destroyed by the radiation field and also probably not formed enough. And you also see that the peak of the large grain emission shifts to a much shorter wavelength and is also a bit broader. And that's understood by the fact that when you have a low metallicity, you decrease the overall abundance of dust grains. And so it means that you have less shielding, and so the radiation from the stars can penetrate deeper into the ASN, and you have overall a hotter environment. Now, if you look at this second parameter, so the effect of star formation, again, the same type of panel, you see that for a solar metallicity, this time star-busting galaxies, you have something that looks like that. So you see that now the emission from a star-busting solar metallicity galaxy is quite different from what you see in the Milky Way. And if you try to decompose it, you're going to see that you have a component that looks like the Milky Way, plus a component of hotter grains that emit at this wavelength, around 40 microns, something like that. I mean, it's a spectrum. That comes actually from hot equilibrium grains in H2 region, so that grains that are heated by the star formation. And again, if you look at the same type of galaxy, but at lower metallicity, so it's a low metallicity star-forming galaxies, you have about the same effect here, but you have also a much wider SCD because you have a lot of star formation that really hits the dust at very high temperature. So now, in terms of emission, what's interesting also is to zoom on the mid-infrared wavelength, because that's what the JWST is observing right now. So here I'm showing you the actual spectra of galaxies at mid-infrared wavelengths, so that's the emitted flux. And you see, so here I'm showing you 1097, which is a rather normal galaxy with a low luminosity AGN. So its mid-infrared spectrum looks like a typical galaxy, solar metallicity galaxy. So you see that it's a zoom on what I showed you before. So you have the continuum from the hot grains here, and you have the mid-infrared features that are here, plus several lines that I have noted, but I'm not going to discuss them. On the opposite, if you look at Central USA, which is an evolved galaxy with a relatively strong AGNs, you see that you have a flatter continuum because you really see the contribution from the AGN itself, and you have a deep absorption feature by silicate. That comes from the fact that you have a strong background source and you have dust in front of it. And on the opposite, if you look at a low metallicity galaxy, you see that you still have a strong hot dust continuum that really comes from the fact that you have a lot of hot dust heated by the stars. And as I showed you before, you see that you really deplete the intensity of these aromatic features. And what's interesting is to look at the evolution of the strength of these aromatic features with metallicity. And here what I'm showing you, it's so it's a way to quantify the strength of the aromatic feature with, so it comes from an SCD fit. So that's a mass fraction of small amorphous carbon grains, so that are carrying those aromatic features. And here I'm showing you first as a function of the intensity of the radiation field. So parameterized by this parameter U that I told you before, that is equal to 1 in the solar neighborhood. And those points, each one of these points, correspond to one galaxy of the Dustpedia sample, which is a sample of 800 nearby galaxies that we have studied. And you see that it's quite scattered, but you have a general decreasing trend of the mass fraction of this grain with radiation field. And I think we understand quite well this trend. It's because when you increase the radiation field, you tend to have more UV photons that are able to destroy those small grains that are the smallest and the most sensitive to evaporation by the radiation field. So that's the Milky Way here. And then you can compare to what happened to the same parameter if you look at how it varies with metallicity. So here the metallicity, I've expressed it as just the abundance of oxygen over hydrogen. And the trend looks like that. So you see you have a rising trend of this parameter with metallicity. And so there are scenarios with that too, but you see that you have a degeneracy. We are not sure which parameter really is the driver. So there are different scenarios in the literature to try to explain this kind of trends. So the first one is the fact that, as I told you, at low metallicity, you have a lower screening effect. So hard UV photon from young stars can more efficiently destroy those small grains. So that would explain why at low metallicity, you have a lower abundance of those small carbon grains. And you can see it spatially, actually, if you look at a typical star forming region. So that's N11 in the LMC. What I show you here, it's a map of the star formation, the radiation field intensity derived from SED modeling. So you see it's brighter in the center here where you have clusters that are embedded. And if you look at the morphology of the same region, but this time looking at the mass fraction of those small carbon grains, so this parameter that I was showing you before, it's the exact opposite. So where you have a lot of UV photons, that's where you deplete those small grains and that you carve their distribution around those embedded clusters. So that's a first possibility. Another one that I proposed a long time ago is that, and actually those different scenarios that I'm discussing here are not necessarily exclusive. They can actually be combined, and we don't know yet what is the truth, but the fact that if you look at evolution of galaxies, a lot of the carbon actually is injected by AGB stars, and the AGB stars have a long lifetime, so it means they start injecting the elements in the ISM after a few 100 million years. And so this delayed injection could explain the fact that at low metallicity, you have less carbon grains that are formed. However, I don't think that's a process that is efficient enough. I mean, that's sufficient to explain what we see, because what we see in the ISM is that you destroy the carriers, I mean, those small carbon grains quite easily. And so it means that you need to reform them also in the ISM. So the pure stellar explanation is not sufficient to my mind. Then after, you have another scenario that explains the origin of these small carbon grains by the fragmentation of larger carbon grains. And so there is a model that shows that is likely. The problem is that this model tends to show a wide scatter with star formation history. So it means that it cannot really reproduce what we see in galaxies accurately. And then after, a more empirical explanation is that the fact that those small carbon grains could actually form in molecular clouds, probably by by bottom-up chemistry, but that's difficult to constrain. So at the moment, we don't really know what is the driver, but what is clear is that those small carbon grains depends on metallicity and on star formation activity. Now, if you look at another wavelength range, so the more the UV visible range, and you look at the extinction curves, you can see that here I show you as a function of wavelength the extinction, so it's expressed as an attenuation normalized in V-band. So V-band is here around 0.55 micron. And if you look in the Milky Way, you have a diversity of extinction curves that are parameterized by this RV parameter. That is simply the slope of the extinction curve. So you see, I show you different curves coming from the Fitzpatrick 2019 survey. And so you have these different features. So first you have the far UV rise. That is this steep slope here. That is essentially due to the absorption by the smallest grains. Then you have this 2175 angstrom bump. That is this feature here that we really see everywhere in the Milky Way. And that is attributed to extinction by small carbon grains that have sp2 hybridized bonds. So it's essentially carbon grains that have also aromatic rings. And you have a knee here, which is also another feature that we don't see very well here, but that is seen if you flip the representation, that is due to essentially the scattering by large grains. So in the Milky Way, you have this type of range of extinction curve. So now extinction curves are measured by looking at towards usually a star, and really looking at comparing the spectrum of a star that is not extincted to what you see, and the difference is going to give you this extinction curve. We can do the same in the LMC and SMC, but we cannot really go beyond that because we have trouble resolving individual stars. So if you look in the LMC, you have some sightlines that are extinction curve that actually look like what we see in the Milky Way, but some that are a bit steeper and with a weaker bump. But if you look in the SMC, you really have something really completely different that goes out of the range of the Milky Way. And I mean, that's well known and it's well seen. And I also show for comparison the Calzetti starburst curve. That is not an extinction curve, it's an attenuation curve. So it means it doesn't include only the dust property effect, it also includes the topology effect, the way you mix the stars and the dust. But so the metallicity effect on the extinction curve is essentially the fact that the bump is lower when you get to a lower metallicity, at least when we look at the trend between Milky Way, LMC, and SMC. The lower the metallicity, the smaller the bump is. And the explanation that makes more sense is the destruction of the small carbon grains. So those are the same small carbon grains that I discussed before about the aromatic features, likely. So in a sense, it's consistent. When you go to lower metallicity, you have a lower abundance of small carbon grains. And also, you have a steeper far UV slope. And that's, there are different models, but the consensus is that also it means that at low metallicity, you have an enhanced abundance of small grains. And you can explain this abundance of small grains by the fact that you have a larger number of supernova shock waves that are going to shatter the grains and so make smaller grains. Then you have another set of observables that are the the elemental depletion. So I'm first discussing it in the Milky Way. So elemental depletion are a quantity that are the difference between the abundance of a given element E, so it can be oxygen, carbon, anything you want, that is observed in the gas phase. So when you do a regular spectroscopy measurement in the gas, minus some estimate of the total abundance. So that's quite a bit tricky to get, but it can be estimated either from the solar value or from the abundances in meteorite, or I mean, you have different standards. But you make this difference because you look at the total minus what's in the gas, and so it's supposed to give you what is in the dust. So with those elemental depletion measurements, you can have an estimate of the mass fraction of each heavy element in the dust. And also, observationally, we see that the trend of this elemental depletion for all elements can be parameterized by a single parameter called the depletion strength that I'm going to discuss later. So if you look at the typical amplitude of depletion, so this parameter AE, that tells you how much an element is going to be depleted, as a function of its condensation temperature, you can separate it into two broad categories of elements. The one that are volatile, so the one that are going to be easily removed from the grains and so be found preferentially in the gas phase, and the one that are refractory, that are on the contrary going to be essentially locked into grains. And when you look at the different elements, you see that you have a decreasing trend because of what I told you. The higher the condensation temperature, the more the element is going to be locked into the grain, and so the less variation you're going to see in its depletion. Now, if you look at the elemental depletion for different elements, you see carbon, oxygen, magnesium, and so on. in the Milky Way, we have the following measurement. So that's what we see in the dust. So that's really what derived from the depletion. So you see it's dominated by carbon and oxygen. And if you look at what is in the gas, you have the green part and the total, so it's total ISM. So what you notice from that is that also a lot of the mass is in silicate. Actually, most of the mass of silicate is in oxygen because it's in the formula for silicate, the basis, it's SiO3 or 4, depending on the type of compound that you have. And what's important to note is that the two main elements that constitute most of the mass of the dust are actually elements that are volatile, that are also a lot in the gas phase, and that are easily removed from the grains. And so that tells you right away that dust is going to be a component on the ASM that evolves a lot, because you can easily remove its main constituent and put them back together. And another way to see that, to notice that dust evolves a lot in the ASM, is to look at the way this depletion factor F star that I just discussed before varies, for example, with the average density of the ASM. What you see is that when you measure towards different sight lines, you see that you have a higher depletion factor, so you have a higher amount of depletion when you get to denser and denser ASM. And this correlation can be well explained by the fact that you need to have a rapid grain growth in the ASM, so you need to be able to accrete gas phase element onto grains and also remove them, so essentially destroy this grain by shocks. Which means that the consensus is that most of the grains in the Milky Way were actually formed in the ASM, because you have this rapid evolution, and the typical timescales of evolution tells you that about 90% of the grains at least should be formed in the ASM. So if you look in the Magellanic Cloud, so there are systematic differences. So you also see clear variations of depletion. So it means that you also have a need for grain growth in the ASM. So the patterns can be compared to the Milky Way. And in the LMC, you see essentially that you have just a scaling of the abundance by the metallicity, which is about 1/2 in the metallicity. But in the SMC that have a metallicity of about 1/5, you start seeing systematic differences, and the fact that they don't apply to that. And here I'm showing you the figure. So that's the solid phase abundance. So that's the depletion, of iron and silicon. And you see that's the Milky Way, the LMC, so they are in this region, and the SMC, you have sight lines that are really difficult to explain with the typical stoichiometry that you would need in the Milky Way or the LMC. And the main feature of the LSMC is that you have almost no silicon into dust, I mean, with an error bar, but you have a strong iron depletion. And then, so I'm going to go a bit faster, but I told you about this sub-millimeter excess. So I'm showing you again this figure I showed you before. So the actual amount of extinction that you have in the sub-millimeter in galaxies is not very well understood. And so this sub-millimeter excess, so myself and several people, I've discovered it almost, 20 years ago. So it was seen essentially in the SED of dwarf galaxies. So I'm showing you again, the dust emission, and you see the observations are here. And so that's the free continuum. We have corrected for the CO lines, for the, all the background contributions. And we are left with a sub-millimeter excess that you can see here. That is systematic. So it's always an excess. We rarely have a deficit, and we see it in many galaxies with different instruments and at different wavelengths. And if you even look at the way this sub-millimeter excess varies within the LMC, so when we have some angular resolution, so I'm showing you again, here it's the surface, the luminosity per unit area. of different regions in the LMC that are characterized by their surface density. So here it's a relatively dense regions. So you see the excess that you would see at 500 micron is virtually zero. But when you go to fainter and fainter regions, so regions where you have a lower density, you see that you have an excess that increases. At 500 microns, it can be really significant. So there are several attempts in the literature at explaining this submillimeter excess. So it's a phenomenon that is quite real, as I told you, that has been confirmed by several studies. In the Milky Way, we see this excess at 500 micron that also decrease with surface density, so the same trend as with the LMC. And since it's an excess, it's always relative to a model. And so it's important to really use state-of-the-art dust models to have a reliable baseline to really compare it. Otherwise, it can be really, I mean, anything. And there are several scenarios that have been proposed to explain this excess. So the first one, it could be a component of very cold dust, so very hidden in cold clumps, that could account for a large fraction of the mass. However, this original explanation is inconsistent if you look at the way it varies in the LMC, because in the LMC, you see that the distribution of this excess is quite diffuse and is anti-correlated with the surface density, so it doesn't make sense. Another one that is really a pure solid state process, it's a model that explains the fact that you could have actually a temperature-dependent optical properties, that if you have a higher temperature, you would change the slope in the millimeter. It's in amorphous grains, and that's consistent with laboratory data. But the model itself still has to be proven, but it actually can explain the amplitude of the excess. But it has trouble to explain the spatial trend, so the way it varies in the LMC. So you have also a competitive explanation, so by Drain and Hensley, that relies on the particular emission of magnetic inclusions, so metallic magnetic inclusions into grains or either as free particles. So there are polarization tests, but it's difficult to explain the spatial trends because the intensity of this excess would be less dependent on temperature. And finally, so the spinning grains that I showed you in the centimeter have also been proposed to explain the excess. But the problem is that it would need to spin too fast, so beyond the rupture of the grain, to really explain the submillimeter excess that we see in some galaxies. So it's not satisfying by itself, and we don't know yet what is the actual explanation. And so to go into that direction, we have recently obtained some NICA2 data at 1.12 millimeter of a few dwarf galaxies to really have a better coverage spectrally and also use some spectral resolution. So that's a project that is in progress. So now I'm going to use the last few minutes to talk to you a bit about dust evolution. So as I told you, if you look at the way dust evolves in the ASM, so when you have star formation, you form stars of different masses, low mass stars and high mass stars. These stars evolved with different timescales. So you have supernova for the massive stars, and AGB stars have a longer lifetime evolution. But what's important is that at the end of the lifetime, these stars are going to produce some amount of grains in their ejecta that are going to provide the grain seeds for evolution in the ASM. And so in this ejecta, you are really going to condense dust, so from atoms, make dust. Then in the ASM, you are going to have a grain growth process. So it means that you are going to accrete gas phase atom onto grain to make more dust mass. Supernova, as I told you, will have a sputtering and shattering effect. So sputtering is when you have an energetic atom that removes some mass from the grain, while shattering is that when you have collision between grains that change the size distribution. So you have also some important processing by UV photons. So you have desorption. When you have a UV photon, you can remove an atom. You have also sublimation, so you can really totally evaporate the grain. You have a cycling between these different phases. And finally, when you go into denser regions, into molecular clouds, you start coagulating the grains, and so changing their optical properties, and also making icy mantles. And you look at with abstraction. So you have equations that dominate the dust evolution. So since I'm a bit short in time, I'm going to skip those equations because they are a bit technical. I'm just going to show you the final result. So yes, so I'm just going to show you the way we model dust evolution. So as a function of time, how the mass of a galaxy evolves in different components. So that's the present time you see for typical Milky Way type galaxies. So you have the typical SFR that's been used for this simulation. And if you look at the gas mass, so it starts from a given value and it decreases because you are depleting it for star formation. The mass of stars, it's the opposite. It starts at almost zero, and then it's constant. The two are constants, the sum of the two. If you look at the mass of heavy elements, so it has a more complex shape. So it rises with time, and after it decreases because of the contribution of dust. And if you look at the dust evolution, you have a first branch here that is quite, low. And then after you have a sudden rise, and you have a regime, and the difference between the two, it's about a factor of 2 at the end. So that's the way we understand dust evolution. And you can play on different dust parameters. So for example, if you increase the efficiency of condensation of dust into supernova, you are going to increase the contribution at early epoch. If you decrease the efficiency of grain growth into the ASM, you are going to really have, almost no dust at present time, because most of the dust is formed in the ASM. And if you decrease the destruction by supernova shocks, most of the heavy elements are going to be into the grains, because you are not going to replenish the heavy element content of the gas fast enough. So if you look at dust scaling relations, so here it's the specific gas mass, so m gas over m star, and that's the dust to gas mass ratio. For different galaxies, so I'm showing you data from the same dustpedia sample that I show you here. You have this type of trend, and you can look at the same trend with metallicity. So you have another scaling relation. And what we did is that we used the model that I showed you before to fit those typical scaling relation trends. So again, the same with different colors. And here I'm showing you the envelope of all the models for all the galaxies. So it's just a probability density distribution of dust evolution tracks. And with that, we can constrain dust evolution parameters. And so I'm going to pass that too. And what we see is that we can constrain the typical time scale for different parameters. So that's the metallicity. So you see for the destruction by shocks, we see something that is quite scattered and that doesn't evolve much with metallicity. For grain growth into the ASM, we start around 1 gigayear, and for the Milky Way, we are an order of magnitude lower. So we show that you have a higher efficiency of grain growth by at high metallicity, and for the condensation in supernova, it's even more dramatic, and you see that at Milky Way you get a trend that is larger than the age of the universe. So it means that this process is really not efficient. The condensation of the grain by supernova is not efficient at high metallicity. So at solar metallicity, we see that we have a rapid grain growth and destruction. And at low metallicity, we see that the dust formation is dominated by supernova. And that's important because it can be, so I'm going to skip that, it's going to be, it's something that is really important for high redshift galaxies, because it means that you can form grains quite rapidly. So on timescales, typically of less than 100 million years, as long as you have a metallicity above typically 1.5 solar. 1/5 solar. And so yeah, so that's more or less what I show you here. I show again one of the scaling relations for nearby galaxies, and those distant galaxies actually fall in the range of low metallicity galaxies around the critical metallicity. So I'm going to summarize here. So what's important is that you have a hierarchy in all what I showed you. You have a hierarchy of the studies. So in the Milky Way, that's where you have the best linear resolution, comprehensive observable. So that's where you develop dust models. Nearby galaxies, that's where you understand the effect of metallicity and star formation rate. That's where you get statistics so that you can constrain dust evolution. And distant galaxies are also important because it really probes galaxy evolution. It can also, at some point, give us access to really truly primordial systems, and so better understand galaxy evolution. I mean, especially the early phases. So what we have learned so far, so I'm going to go fast on this summary because I'm out of time. But as I showed you, metallicity and star formation activity are really the two main parameters that influence those properties and SEDs. At low metallicity, we have a deficit of aromatic features, displacement pattern change at low metallicity, and we have a submillimeter excess that is also enhanced at low metallicity and low surface density. And for the dust to gas mass ratio, there is a nonlinear trend with metallicity that is explained by the dust evolution, which is the fact that dust evolves constantly. So it's mainly formed in the ASM at solar metallicity. But at low metallicity, it's really due to supernova condensation. And the next challenges are to account for local dust evolution, build extragalactic dust models, as I showed you, and solve this degeneracy that was everywhere. I compared the two between metallicity and star formation activity. And get statistics at long wavelengths. So the main opportunity that we have are these large observatories, so ALMA, JWST, and maybe PRIMA. I'm trying to get interested into that, except that PRIMA will have a quite low angular resolution. So in the end, ideally, we would need a high angular resolution for infrared project. And just if you want to read more, I can recommend these two things by myself. So thank you, and sorry to be a bit over time.
Thank you very much, Frédéric. This was very, very thorough, very, very thorough. I would just suggest to leave the last slide on so that people can take a note of that.
Okay.
Just because it was
yeah, sure.
Both the annual review and in particular the book that you wrote, using your as there is an excuse.
Yes, as a motivation more than an excuse. Yeah.
As a motivation. Yeah. But anyway, no. Yeah, these are both excellent. Yeah, thank you.
So thank you very much. Is there any question? Nick, yes, Nick Kilafis.
Yes. Thank you. This was an excellent talk. I had seen your book, and now hearing it directly from you was really amazing. Thank you very much. It was really a treat. Maybe I missed it, but in the slide with these galaxies, the nearby galaxies, I did not see NGC 891, which has been studied a lot. Regarding its dust distribution properties and so on. Not in the direction that you have gone, but is there any reason that this galaxy is not in your list?
So you are mentioning about the slide where I show different galaxies as a function of distance and metallicity?
That's right. Starting from the nearby one and going.
I mean, so actually, I'm working on several papers about NGC 891 in the Imagine collaboration, which is a granted time NICA2 program. And so we have a PhD student that is just submitting a paper about it. So I mean, this galaxy is very interesting. Sorry, I missed it. But I don't even know why it was not there. It's just I chose a few galaxies that are representative. Yes, I went too fast. But yeah, no, I mean, there's no particular reason. This is a galaxy that is very interesting. And so we also have, I'm part of a JWST program that we have some data of this galaxy. And we're interested in looking actually at what happens in the ejecta, above the disk and below. And we see actually those plume of dust ejection. So we can really compute dust evolution timescales and the relation with the winds of this galaxy. Yes, the figure is here. Yeah. No, maybe I should add it, but it was already too crowded, so that's why it was done there.
Yeah, this is what I meant, but okay, that's fine.
Yeah.
Vasilis?
Yeah, Frédéric. Yeah, these are very, very interesting results. I was just wondering if you could comment a bit now. You showed in the introduction a bit of your slides, all these uncertainties about the extinction curves, right?
Yes.
What we use, and now people with JWST, they would be applying as at least first order of magnitude corrections, extinction curves to their data, right? What can we say about that? Has the field a bit evolved? Because as far as I know, and David probably knows better, people in a sense, they use a sort of like an ad hoc approach saying, well, assuming a Calzetti extinction curve or an LMC just because that this galaxy is smaller. Do you think there is any room for improvement on those? Because in particular, the presence of the bump or not has also, effects in not so much in number count studies, right? But as Veronique had shown, for example, in the interpretation, at least, of the properties.
So, there are several things. First, so these extinction curves, first you have extinction and attenuation. So, as I try to explain, extinction is really what is due to the intrinsic dust properties, and attenuation is when you start also having the effect of how you mix stars and dust together. So the Calzetti, it's an attenuation law. It accounts for the assumption that you make about the geometry. So that's another parameter. But so there are uncertainties about extinction curve, but there is also a lot of variability. The range of extinction curve that I showed in the Milky Way is it's not due to uncertainty. It's really that there are variations within the Milky Way, and that are understood as variations of the dust properties in different environments. So they depend on this RB parameter, which is also related to the column density of hydrogen. And it's linked to the fact, so you see this diversity depends on the density. So if you go down, you go towards a denser environment. And because you are seeing the effect of grain growth and at some point coagulation too, that changes the size distribution and the grain properties. So that's something that is seen everywhere within the Milky Way. And if you want to do that better outside the Milky Way, you have to make a model where where you take that into account, and which is very difficult, I agree.
So in essence, oops. Sorry, I pressed something, I don't know. So in essence, if I were to do some sort of like SCD fitting with a correction in the optical, the ideal approach would be to sort of like give different plausible scenarios for all these type of curves.
So that would be a way that you could at least get a sense of what is your systematic uncertainty. But the best way to do it would be to really have a model of your galaxy and try to make some relative transfer estimate of the actual attenuation, taking into account the fact that you would have different dust properties in different regions. So, for example, if you make a model of galaxy where you have diffuse ASM and dense clumps, you would generate an attenuation that would have different dust properties, and so different extinction curves in the diffuse ASM and the clumps. You see what I mean?
Yeah, but not very many people who do distant galaxies do that, right? Unless
but even nearby galaxies, we can't do that. I mean, it's very complicated. I've been trying to get a project funded about that, and people don't believe in it, that you can do these kind of things. It requires a lot of modeling, you know, a lot of assumptions. So you need to generate large grid of, you know, distribution of matters. You need to do relative transfer into them, and you need to try to understand what are the parameters that are really relevant, you know, the global parameters, so the filling factor, the typical density of the clouds, the age of your stellar populations. And even with such a complex modeling, you know that you are still going to be a bit wrong yet, you know. So that's why it's quite difficult. Yeah. But about extinction curve and JWST, so Carl Gordon recently published, you know, like a universal extinction curve from the UV to the IR. That is supposedly well calibrated, but there are still some debate about how you stitch the optical part to the infrared part of the extinction curve.
Okay, thank you.
I see David has a question.
Yeah, well, no, I just wanted to comment on that. Sorry, there is a background noise. Indeed, for the distant galaxies, we don't have enough information to really model all the different regions, but what is puzzling is that there are effective extinction curves that work quite well. For example, when you compare the far-infrared or UV ratio, that is in some sense a bit puzzling. Although you always have these outliers of very, very obscure galaxies, and where even, I mean, where we have nearly only infrared emission and no UV or optical coming out at all. So where it's extremely difficult to constrain the extinction curve. But how do you understand the fact that despite the complexity we see in the Milky Way, there is something analog to the IMF, which there are so many reasons to have a varied IMF in various regions, and in the end, galaxies look as if they had the same IMF. It seems to be with the same that you have a kind of effective attenuation law that works relatively well, even though you have many reasons to think that it shouldn't be the case. What is your opinion on that?
I mean, it's difficult to say, but I would say that it's just statistical mixing. You know, when you start to have to take into account a whole galaxy, which is really a mix-up of complex regions, you are going to average out the differences between the different regions and get something that is closer to an empirical average than what you would get if you were really trying to resolve individual regions, you know, like diffuse regions or a molecular cloud. I guess it's because you are mixing everything that you are getting closer to an average. Yeah. But I guess it will also, maybe there's also a selection effect, that the galaxy that you are talking about are probably quite starbursty, you know, have a relatively high metallicity. Now that with JWST you can really detect low metallicity distant galaxies, maybe you are going to see systematic differences, possibly, you know, in that range. I don't know if you already have some data about that.
Well, it's starting, but I don't know yet if we have enough information over the whole wavelength range, but possibly in the near future, yes.
Okay, if there are no more questions, then I think we can thanks again, Frédéric, for the nice talk. And okay, so I will stop recording here.